4.4, we're going to talk about indefinite integrals, and we're going to talk about the net change theorem. Now, we have here an example of an indefinite integral. It's indefinite because there is no lower limit, there is no upper limit given to us. So what this is going to result in is, according to an integral, I'm supposed to first of all take the antiderivative of the function. The antiderivative here is natural law of the absolute value of x. And then I'm supposed to plug in the upper and lower, but I don't have those. And so all this is going to result in is the antiderivative, the general antiderivative. And that's why we have to remember to include the plus c. So that is an indefinite integral. On page 322, you can look and see a table of indefinite integrals. It's the same as a table of integrals. It's just that the roles of the derivative and antiderivative kind of switch roles from previous derivative tables. So very similar table to what you've seen before in terms of derivative, just kind of in reverse order. Now, let's take the antiderivative of this. It's indefinite again, no lower, no upper limit. So the antiderivative of 12x to the fifth, 12x to the sixth, divided by 6 minus coefficient of 2, you come along for the ride. And what is the derivative of secant tan? Well, secant tan is the derivative of secant. So the antiderivative of secant tan would be the secant, in this case of x. And since this is indefinite, general antiderivative plus c. And we would probably want to clean up this 12 over 6 and just call it 2. All right, so that is the indefinite integral. We got another one down here. Now this one is not indefinite, this one is definite. But how are we going to do something like this? Well, just as a reminder, whenever it's possible, I should have a dt here. Whenever possible, we're going to simplify. So we're going to take 2t squared divided by t squared, we get 2. Plus, when we do this division, we're going to get square root of t, or t to the 1/2. In this one, we've got minus 1 over t squared, which is t to the negative 2. So we simplified this. We still need to find the integral between 1 and 9 dt. Well, the antiderivative of 2 minus the antiderivative of t to the 1/2, t to the 3/2 divided by 3/2 or times 2/3. And sorry, this is t to the negative 2. So I'm going to start out by saying minus. I'm going to say t to the negative 1 over negative 1. And if I'm going to divide by a negative 1, that's going to essentially turn this into a plus sign. And then I want to evaluate this between 1 and 9. That may be helpful for me to refer to this t to the negative 1 as 1 over t. And now let's drop that 9 in here. And 2 times 9 is 18. Minus. Drop the 9 in for this term right here. Remember what 3/2 means. It means let's take the square root of that number and cube it. So the square root of 9 is 3. 3 cubed is 27. 27 times 2 is 54. And 54 divided by 3, 18. Plus, when we drop that 9 in here, we get 1/9. Well, that's not a difficult sum to find. We're going to subtract from that. Let's drop a 1 in here. You got 2 minus 2/3 minus 1. So we've got 1/9. Now I think we're probably going to have a common denominator of 3, so I'm just going to jump right in there and call this, a common denominator of 9. 1/9 minus 2 minus 2/3 minus 1. I think that gives us 1/3. So 1/9 minus 3/9. I believe we're going to end up with negative 2/9. So you're ready to have to simplify, because there is no quotient rule of integrals. Okay, the net change theorem. Net change theorem is something that shows up pretty often on the AP exam. And what the net change theorem says is the integral of a rate, and I'm going to underline that word rate. And you guys got to press pause to write this down. You go ahead and do it. The integral of a rate at which a function changes. So this is the rate. This is the integral of a derivative of a function, or the rate at which a function changes. The integral of that derivative is the net change, also known as total change, in the function itself. So up here we're taking the derivative, taking the integral of a derivative. Let me call it r primed of t, from a to b. That equals the change in the original function, the change in r of t between the values of a and b. So when you take the integral of a derivative, remember the amount that the original function is changing. So the integral of acceleration, well, that's the derivative of velocity. So that's going to tell us how much velocity changes. The integral of velocity. The integral of velocity, well, velocity is the derivative of position. So that's going to be a change in position. And if we want distance, and we'll practice this with calculators, if we want a distance traveled, we just got to make sure that all of these changes in position turn out to be positive. To do that, we take the integral of the absolute value of velocity. All right. So if we want to find a change in position, that's what displacement is, we'll take the integral 1 to 4 of 3t squared plus 2t minus 6 dt. When we do that, and feel free to use your calculator. Why don't you go ahead, use your calculator right now. What you should find, put this in the calculator correctly, you should find that you end up with 60 as your displacement. Now, if you do the same thing to find distance, integral from 1 to 4. But now we want absolute value of 3t squared plus 2t minus 6 dt. Now remember, to put that into our calculator, we again have to do math 9 to get our integral. Now to get absolute value, I'm going to press second and then the 0 key. That brings up the catalog. And the first thing in catalog is absolute value, so then I'm going to hit the enter key. And that will give me the absolute value. That's when I will be typing in my function here and my dt. Now, if I do that and do that correctly, and you should do that, and if you got to press pause, do it. Should end up with 60.121. Make sure that you can do that. That is a nice shortcut to find distance. We don't have to go from the beginning of the integral to where we stop, from where we stop to where we stop again. If we do from where we stop again to the end of the interval, we aren't going to have to do that if we use the absolute value of velocity. All right, the acceleration of an object is given to us, and an initial velocity of -5. And we have the time interval from 0 to 5. Let's find the velocity in any time. Well, velocity is just going to be the antiderivative of acceleration. So the velocity in any time is going to be 2t squared minus 7t plus some constant. And if we know that the velocity at a time of 0 is equal to 5, well, we got 0 minus 0 plus c. We realize that c is going to have to be, sorry, that was -5. c is going to have to be -5. So let's turn this into a -5. So there's our velocity. Now let's find the distance traveled, and let's practice that second 0 enter, or that absolute value. We're going to have the integral. Oh boy, a little jumpy. We're going to have an integral that goes from 0 to 5. We're going to have the absolute value of 2t squared minus 7t minus 5 dt. And take a moment with your calculator and figure out what that is by pressing pause. Did you get 30? Whoopsie. Did you get 37.609? That's what came up on my calculator. I'm going with it. That is how far we traveled, and no units were given. None would be expected then in the answer. If there were units given, units would be expected. All right, marginal revenue. Marginal revenue is the derivative of revenue. And the revenue function is called R of X. X is the number of units sold. So what does the integral of this rate, what does the integral of derivative tell you? And I got to be specific. Got to use these numbers as I try to describe this. Well, anytime we take the integral of a rate, we're going to say the net or total change. So I'm going to say the net change. You said total change, that's just fine as well. Total change in. Now, R primed is the derivative of what is changing, and what is changing is the revenue. So as long as I know what this is the derivative of, I know what's changing. This is the net change in the revenue. This is from the sale of unit 1,000 to unit 5,000. So I got to be specific. I got to use that upper and lower limit. So net change in the revenue, and we've got to be specific about when that change is occurring. What are the parameters of that change? When we sold 1,000 to the 5,000th unit. All right. And finally, it's a typical kind of question you would see on the AP exam. At a time of 2 hours, there are 700 bacteria on a microscope slide. Population is changing, and we are given the rate of change in the number of bacteria, and that's in bacteria per hour. How many bacteria will be on the slide at a time of 8? Okay. First of all, where are we starting? Because wherever we start, plus the amount that something changes equals the end result. And again, this is something that will be on the AP exam. Now, it's possible that they give you the end result and they tell you where you started and you got to figure out how much things change. They might tell you the end result. They might tell you how much things change or give you enough information to figure out how much things change, asking you to figure out what was the initial amount. So this question could be asked a number of different ways, but the way it was asked here, the starting amount is 700. And then things change between the 2nd hour and the 8th hour. And to find out how much things change, we take the integral from the 2nd hour to the 8th hour. The integral of the rate at which things change, 5.7x squared minus 4x dx. And that's going to give us how many bacteria are on the slide at a time of 8. So you can press pause, put that into your calculator, and see what you come up with. When I did this, I got 700. I believe this was 837. 837.6. Now we're talking about living things, these bacteria. So I think I would round up. When I get 1,537.6, I think I would round that to 1,538. I think if you truncated it, you wouldn't be wrong either. And since units were given, I'll supply units as part of my answer. So that's how we're going to use the net change theorem, or the total change theorem. What we start with, plus how much things change, to give us the end result. Or n minus change will give us our starting value. And a lot of times they will be asking, what was the initial value of this function? All right, assignment time. Good luck.